How do you measure mass on the International Space Station? Good morning, ladies and gentlemen. Welcome to class. Let's do this. I want you to start off by going to page 258 in your textbook. You should have your book by now. If you don't, go to the library, get it. You're going to read example 6. You're going to stop over here.
Cool.
Okay, now that you've stopped, let's talk about what you read. So ultimately, let's take a look at this picture right here. Ultimately, we can see that we have this spring-mounted chair here that the astronaut would sit in, and the chair will oscillate back and forth. It has a spring in it, and it creates what's called simple harmonic motion. We haven't talked about that yet, but we're going to be talking about that in January.
Most of this reading won't make sense, but that's okay. You'll get it later.
Yeah, it's just about getting through it right now. What will happen is it's going to oscillate back and forth. It'll move back and forth, and it will have a specific period. And they can use that to, it'll convert it directly into the astronaut's mass. I'd like to direct your attention to this side if you're like, Miss Moore, how come we used t squared? Well, in order to find the mass, you can see over here, we've got this t squared right there. The k is a constant, 4 pi squared is a constant, so essentially this t squared right there, that square is the reason why we squared the time for our washers.
To get a straight line.
To get a straight line.
That's
So, all right. I think that'll work. There we go. Next question. Why does the blade go back and forth?
Why do it do that?
Let's answer it. My next question, what determines how much force the hacksaw blade exerts on the washers? So the hacksaw blade on the washers. So think about a rubber band. If I just pull it like this, I'm not putting much force, right? And it doesn't go very far. But if I pull it like...
Don't hit me, don't hit me!
Oh my God! Let's try that again.
Don't know it
Don't know my own strength.
Now the farther you pull it back, the more force it exerts.
The farther we pull it back, the more force it exerts. There we go. All right, so the reason why the blade goes back and forth, the first question we want to think about is how much force the hacksaw blade is exerting on the washer, and that's determined by the amount of force. The restoring force, what is that? Restoring force. So restoring forces result in oscillatory motion.
What is it trying to restore, Ms. Moore?
Well, when I push it this way, it goes back that way. When I push it this way, it goes back that way. Where is it trying to go back to?
Right there.
The middle.
It's trying to restore equilibrium.
Equilibrium. So our restoring forces, they're trying to restore it back to equilibrium, and it results in that oscillatory motion, that back and forth motion. That's where we get our period from. Oh, another way we can look at this. Remember the more washers we put on here, the slower the time was, right?
Yeah.
So I've got this weight on here. Let me try that again.
Pull it down about half as much.
So I've got this weight on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Put another one on.
Right?
Put another one on.
So when I put this guy on there, I'll pull it down now. 1, 2, 3, 4, 5. It's slower, right?
It's slower.
So
and that is an oscillation when it goes back and forth. Like
yeah,
that.
and spring here, oscillating. Spring here, oscillating. Sweet. Inertial mass is the property of an object or a system that determines how its motion changes when it interacts with other objects or systems.
What's a system?
What the heck is a system? What is inertial mass? Let's talk about it. The universe is very large and complex. We know this, yes? And science simplifies this complex universe that we live in by examining an isolated part called a system. So the world is complex. Sometimes it's too much to deal with all of it. So we isolate certain parts of it and we call that our system.
Kind of like my life.
Isolated. A system is an object or a collection of objects. Objects are treated as having no internal structure. So again, we're simplifying here. If I was to think about an atom and the protons and the neutrons, or maybe even the quarks inside those, we won't get into that, and the electrons, that's too complex. So if we want to think about it more simply, we could treat it as if it has no internal structure, just like a billiard ball or a pool table ball. Systems have properties determined by the properties and interactions of their constituent atomic and molecular structures. That's a lot of words.
That's a lot of words. Look at all those syllables.
What does this even mean? Let's talk about it. If the hacksaw blade is the system, if the hacksaw blade is the system, what substructure gives it its properties?
Hint.
Well, first of all, what is our hacksaw blade made of?
Hacksaws?
So it's definitely some sort of metal, yes? So the metallic bonds in the hacksaw that make up the metal that makes up the hacksaw, the metallic bonds, metallic metal, between the iron atoms, must be iron, are the result of electrical attraction and repulsive forces. So within our structure, oh wait, let's look at this thing. Let's pretend like this is, oh, broke it now. Okay, within our metal, our iron, pretend like this is part of our hacksaw, right? We have these different, we have metallic bonds, and these metallic bonds between each iron atom, they like to be a certain length, and they go together. They attract, they repulse, they attract, repulse, and what happens is that attraction and repulsion, it acts like a spring. So the bonds, they act like springs, and you can see that, right?
Those are springs.
They are strings, right? Back and forth. The bonds, they act like springs between the atoms in order to maintain this ideal bond length, because they want to be this certain length, right? They don't want to be like rah, right? They want to maintain that certain length, and so the bonds act like springs to maintain that length. So, what produces the restoring force? Right, the restoring force, getting it back to that middle equilibrium part. Whoops. Okay, so we want to be thinking about the metallic bonds in between the iron atoms in here, and how they act like springs. Therefore, this acts like spring. Huh? Cool. But why doesn't the hacksaw blade go back and forth forever?
Get bored?
It's like, do I do this all day? Right? So, why does a paperclip?
Do you have a paperclip?
Do you have a paperclip? First, find a paperclip. Look under your couch. Ask your mom. Ask your dog. Okay. And if you have a paperclip, back and forth, back and forth, back and forth, back and forth.
Bend it. And
oh, nah, more.
And then put it on your lips.
Oh, I'm scared. It gets hot. It gets hot. You want to go hard with it, okay? And when you touch your lips with it, you're gonna be like, oh, that's hot. And so what's happening here? Well, as we're bending the metal back and forth,
Oh.
Energy is being released in the form of heat here.
Yeah.
The other thing that's happening is, well, as this oscillates back and forth, air is being pushed out, and so we lose energy in those two ways. For an isolated or closed system, and let me just say, this is very important, this idea of a closed system. This is going to be carrying on throughout AP Physics. You need to know this. So for an isolated or a closed system, the conserved quantities are constant. So for example, the mass, the energy, the charge, momentum, angular, linear, it's all conserved. It's the same, if mass comes in, the same amount must come out. It's conserved. Whereas in an open system, oh, let me go back for a second. Think about a closed system like a soda, a soda bottle that has a closed lid on it, right? Everything inside is contained. That soda could sit there for a year and it would taste the same. But once you open up the lid, it becomes an open system, one that exchanges with its outside surroundings. So we no longer have the same amount in and out. Instead, we have kind of this constant changing dynamic flow of stuff. So again, the soda bottle is open, and after a year, what's gonna happen to that soda?
Evaporation.
Yeah, it's gonna go flat, whatever's left of it, right? So having an open system that's the complex, that's the complicated. Oftentimes, in science, we think about things as a closed or isolated system. So how could this idea of systems be applied to our hacksaw blade activity? Read pages 79 through 81 to find out and learn more. Also, finish the lab report, and also you should also finish answering the question, what is the mass for one washer? If we haven't already, not sure what I'll do on Canvas when this happens, so I'm just gonna say it just in case.
If you don't have a book, go get one.
You need a book, go get one.